Imagine an AI that, doesn't just solve complex mathematical proofs, but actually opens up its own Python files, deletes its underlying code, and then rewrites its own workflow to get smarter.
I mean, it sounds like complete science fiction, right?
It really does.
Yeah.
But welcome to today's deep dive, where we're actually proving it's not. Our mission today, and really every time we sit down with you, is to crack open these state-of-the-art papers that are literally laying the foundation for generative AI. We want to translate that dense research into, well, the insights you actually need to understand where this tech is heading.
Because it is heading somewhere wild.
Oh, absolutely. And today's source is this fascinating paper from researchers at the University of Pittsburgh and Caltech. And this system, an AI that evolves its own internal logic to conquer formal math, it is an absolute mind-bender.
Yeah, it really forces us to rethink everything about how these models improve, For years, the bottleneck in AI mathematics hasn't just been about raw intelligence or, like, parameter count.
Right, like how big the model is.
Exactly. We've been treating the AI like a brain in a jar, but real problem solving is about how that brain interacts with its environment. Like, how does the system use external tools? How does it diagnose a failure when it hits a wall?
Or how does it plan a multi-step proof without just, completely losing the thread halfway through?
Yes, precisely. This paper shifts the focus entirely. It's no longer about building a smarter brain. It's about building a system that can invent its own methods for using the brain it already has.
So the guiding question I want you to keep in mind as we explore this is, if an AI isn't handed a carefully hand-designed workflow by human engineers, what kind of workflow will it evolve for itself?
And to answer that, we really have to look at the unique architecture these researchers designed. They didn't just give the AI a standard chat interface, they built a very specific kind of sandbox.
Okay, let's unpack this. Because understanding this sandbox is crucial. It's like, well, think of it like, instead of teaching a chef to bake a specific cake, we're putting them in a magical kitchen where they can physically rearrange the oven, the fridge, and the prep stations however they want to bake better cakes faster. So explain the rules of this kitchen. What can the AI change, and what is off limits?
So they split the system into two highly distinct halves. The first half is what they call the mutable workspace.
Mutable, meaning changeable.
Right. This is where the AI has total, absolute control. The AI is given access to a live code environment where it can rewrite its own proof workflow.
Wow.
Yeah, it can open up the Python scripts that dictate how it prompts itself, how it searches for information, how it handles errors, and it can alter those scripts, test them, and just keep the changes that work better.
But obviously there has to be a catch, because if it can change everything, what stops it from just changing the grading rubric to say it passed?
Exactly. And that brings us to the second half of the system, the fixed, trusted runtime.
Which is the part it can't touch.
Bolted to the floor. The core of this trusted runtime is the Lean verifier. Lean is a formal mathematical programming language. The AI cannot edit it, it cannot negotiate with it. Lean serves as the absolute unhackable judge of whether a math proof is correct.
And just to clarify, this isn't like a standard unit test in software engineering, right? Where you can sometimes game the test by just hard coding the output they want.
Not at all. Formal verification checks the logical structure of a proof against fundamental mathematical axioms. It evaluates every single step, line by line.
Oh, wow.
Yeah. So if the AI claims that step B follows step A, Lean mathematically guarantees whether that transition is valid. The AI can rearrange its mutable workspace all day long, but at the end of the day, the proof it outputs has to survive the microscopic scrutiny of the Lean compiler.
Which is a huge deal for you listening, because, we are all familiar with the hallucination problem in generative AI.
Oh, absolutely.
These models will confidently cite fake legal cases, or invent non-existent math theorems, or just smoothly lie to your face. But this architecture creates an environment where hallucination is instantly punished. The AI can't just output text saying, therefore the theorem is proven.
Yeah.
Lean must independently re-verify it.
And that strict environment is exactly what allows for real evolution. But, you also need the right kind of pressure.
Right, which brings us to the training problem. Because if you give a toddler a university calculus exam, they just cry. You get zero signal on how to improve.
Exactly.
But if you give a college student basic addition, they ace it immediately and learn nothing. So how did the researchers solve this difficulty problem? Because looking at the paper, the seed agent-like, the very first generation of this AI only solved 12.7% of the held-out mini F2F math test, which is basically high school math. And it solved absolutely none of the harder competition-level problems.
What's fascinating here is how they engineered a completely organic solution. They call it the co-evolving benchmark.
The co-evolving benchmark.
Yeah, right. Instead of a human trying to guess the perfect difficulty curve, the benchmark essentially operates on a treadmill. And that treadmill automatically accelerates based on the AI's actual performance.
Walk us through the mechanics of that treadmill. Like, how does it know when to speed up?
Well, first, they stratified a massive pool of math problems into 3 distinct tiers. You have level 1, which consists of single tactic, warm-up lemmas.
Just to jump in quickly for anyone unfamiliar, a lemma is essentially a stepping stone, right? It's a smaller, proven statement you use to build up to a larger theorem.
Precisely. Basic logical stepping stones. Then you have level 2, which includes those mini F2F problems, solid high school Olympiad level challenges.
Okay, so a step up.
A big step up. And finally, there is level 3, the Putnam bench problems. These are drawn from the William Lowell Putnam mathematical competition, which is arguably the most grueling undergraduate math exam in the world.
So they have this tiered pool of problems. How do they actually match those problems to the AI's current skill level without breaking it?
They use something called the champion rule. In every generation, the system spawns multiple mutated versions of the AI.
Like digital offspring.
Basically, yeah. Each version tries a different workflow in its mutable workspace. They are all tested against the current benchmark. Whichever agent scores the highest is crowned the champion.
And then its mutated code becomes the new baseline, survival of the fittest code.
Exactly. But here is the critical trigger, the 30% threshold. When the champion of a generation clears a 30% solve rate on its current mix of problems, the system realizes the test is losing its evolutionary pressure.
It's getting too easy.
Right. So it actively retires the specific tasks the AI has mastered and injects harder problems from the next tier up. The test evolves alongside the student.
But hold on, here's where it gets really interesting for me. If the test is constantly shifting out easy problems for hard ones, the raw scores are completely meaningless across generations, right?
They are, yeah.
Because if Generation 1 scores a 30% on basic lemmas, and Generation 10 scores a 30% on Putnam problems, you can't just put that on a graph. So how do the researchers mathematically prove the AI is actually improving and not just getting lucky with different questions?
That is the exact statistical hurdle they had to clear. Because, if the yardstick keeps stretching, standard measurement breaks down. They solved this using a technique called single anchor recalibration.
Single anchor recalibration. Break that down for us.
Whenever the benchmark updates, like when it crosses that 30% threshold and swaps in harder problems, the system pauses the evolution. It takes the exact same champion agent and forces it to take both the old test and the new test.
Okay, so you're using the champion as a constant to measure the variance in the test.
Exactly. By comparing the champion score on the old test to its score on the new test, they calculate a difficulty coefficient, a multiplier, which they call C.
Let's do the math on that just to make it concrete.
Sure. Say the champion scored a 39% on the old test. Then it takes the newly updated, harder test, and its score naturally drops, say, to 32%.
Makes sense, the test is harder.
Right, so you set up an equation. 0.39 times 1 equals 0.32 times C. You solve for C by dividing 0.39 by 0.32, which gives you 1.24.
Okay, meaning the new test is mathematically proven to be 1.24 times harder than the old one, at least for that specific AI architecture.
Yes. And from that point on, every score achieved on the new test gets multiplied by 1.24, allowing an apples-to-apples comparison with the very first generation.
That's incredibly elegant.
It is. And the compounding effect of this recalibration is staggering. By generation 15, that difficulty coefficient had grown to an incredible 3.17.
Wait, really? Let me push back to that for a second, though. Is mathematical capability really linear like that? Does a 3.17 multiplier actually mean the AI is over 3 times smarter? Or is it just a statistical quirk?
It's a completely fair critique, and it's why the researchers didn't just rely on that multiplier. The multiplier is primarily an internal metric, just to keep the evolutionary treadmill running smoothly. To prove actual objective capability gains to the outside world, they always evaluate the agents against a static, held-out test.
A test the AI never sees during training.
Exactly. And we'll get to those explosive results in a second, but I want to touch on something you mentioned earlier, the cheating aspect.
Right, because of reward hacking. If you put an AI in a box and tell it to maximize a score, it will find the laziest, most devious way to make that number go up. If it's generating Python scripts, what stops it from writing a script that just reaches into the grading directory and changes its own score to 100%?
They foresaw that. The trusted runtime acts as an absolute quarantine. The AI's Python scripts are executed in strictly isolated worker processes. It has zero system-level access to the scoring module.
But can it trick the Lean verifier itself? Because, I mean, there are commands in Lean that let you bypass proofs, right?
Yes, and this is where the strictness is paramount. In Lean, if a human mathematician wants to test final logic without finishing every minor detail, they can type commands like sorry or admit.
Basically telling the compiler, skip this part, assume it's true, I'll do it later.
Exactly.
An AI would absolutely weaponize the word sorry to skip the whole test. It would just say, theorem 2 + 2 = 4, proof, sorry, and claim the point.
Which is why the trusted runtime actively scans for and strips out those specific bypass commands before passing anything to Lean. The environment forces the AI to do the actual work. No shortcuts.
Okay, so we have the sandbox, the co-evolving treadmill, the anchor math, and this bulletproof quarantine. So what does this all mean? After 15 generations of evolution, what kind of workflow did the AI actually invent for itself? Did it evolve into this brilliant math professor meticulously breaking down massive theorems into elegant sub-goals on a chalkboard?
No, actually, it did the exact opposite.
Wait, really?
Yeah, it became a gritty, stubborn mechanic.
A mechanic?
Yeah. The evolutionary tree is full of fascinating failures, and the brilliant professor approach was one of the biggest ones. There was a specific agent labeled C141. It actually modified its workspace to create a dedicated Python module called subgoalprover.py.
Okay, so it programmed itself to plan out helper lemmas before tackling the main theorem. That sounds perfectly rational. That's how we teach humans to do complex math. Why did it fail?
Because assembling a final theorem from isolated parts in a formal verification language is just incredibly fragile. When C141 broke the theorem into 5 pieces, those pieces lost the global context of the main problem.
Oh, I see.
Right, so when it tried to stitch them back together, the variables didn't perfectly align with the strict requirements Lean demanded. It's like building 5 custom gears for a watch in completely separate rooms. If even 1 millimeter is off spec when you assemble them, the whole watch jams.
And Lean just rejected it.
Lean simply rejected the final assemblies. Too many points of failure.
So the elegant top-down plan shatters on contact with the strict judge. If the professor failed, what actually worked?
The AI that won out the champion at Generation 15, Agent C144, abandoned that multi-file, elegant structure entirely. Instead, the winning workflows were repair-centered. It favored a highly compact, monolithic repair loop.
Detail the mechanism of that loop for me. How does it operate like a mechanic?
It all revolves around immediate, microscopic feedback. The AI's Python script would take the math problem, generate a full single-shot proof attempt, and immediately submit it to the Lean compiler.
And Lean throws an error.
But not just wrong. It throws a highly explicit compilation error, pinpointing exactly which line of the logic failed and why.
So it tells the mechanic exactly where the engine is smoking.
Yes. The Python script is programmed to catch that specific error string and feed it right back into the prompt context. The AI reads the error, generates a patch for that specific line, and fires it back to Lean. It just loops this process at high speed.
Generate, compile, catch the error, patch, repeat.
Exactly. It traded elegant planning for rapid, relentless iteration.
That is fascinating. It leveraged its speed instead of trying to mimic human foresight. So what were the objective results on that held-out test you mentioned earlier?
The numbers are undeniable. The seed agent started with a 12.7% solve rate on the held-out mini F2F test. Just 15 generations later, using this monolithic repair loop, agent C144 achieved a massive 45.1% solve rate.
Wow, it more than tripled its performance.
Yeah.
And not because the underlying neural network got bigger, but purely because it optimized its own workflow.
Exactly. And to prove the co-evolving treadmill was the driving force, they ran a baseline test. They allowed the AI to evolve its workspace for 15 generations, but they kept the benchmark fixed. They never made the test harder.
And what happened?
The evolution completely stalled out. That baseline run only reached a 32.0% solve rate. Without the hostile environment constantly pushing it out of its comfort zone, the AI just stopped finding more efficient ways to code its loop.
So constraint and pressure bred genuine innovation. I love that. And I want to zoom in on that innovation aspect, specifically regarding the tools the AI used. Because even if it abandoned the multi-file subgoals, it didn't just use brute force, right? It actually invented custom tools to fix its own cognitive flaws.
Yes, and this is where the system showed an almost, well, eerie level of operational self-awareness. One of the biggest problems with these models is that they hallucinate function names.
Right.
The AI realized its repair loop kept stalling because it was trying to call lean math libraries that didn't actually exist. It was reaching into the toolbox for a metric left-handed wrench, realizing it wasn't there, and wasting a precious compilation attempt.
How does an AI realize that and fix it?
Through the mutable workspace. It recognized this pattern of hallucination failures, so it spontaneously evolved a tool to build a guardrail. Yeah, it wrote a Python script designed to ping the lean environment, pull a list of valid verified function names, and store them in a local cache. Then, it updated its main workflow so that before it ever submitted a proof, it would cross-reference its own code against this cache.
It basically built its own custom spell checker for math commands to stop itself from hallucinating. That is wild.
It really is. It didn't need human engineers to notice the problem and write a patch. It engineered the patch itself.
So the big takeaway for you listening to this deep dive is that in a tech landscape obsessed with scaling, feeding models more data, adding trillions of parameters, building massive data centers, this paper proves there's an entirely different vector for advancement.
It's the difference between buying a bigger engine and learning how to actually tune the engine you already have.
Exactly. The future of AI isn't just about massive generalized models. It's about placing these models in highly specific, mutable workflows with co-evolving challenges. It's a shortcut to understanding the next frontier of self-improving systems.
And for anyone feeling overwhelmed by information overload or AI hallucinations, this framework is the perfect antidote. It proves that AI can be rigorously trusted, but only when we force it to ground its work against hard, verifiable facts rather than just letting it talk.
Constraint breeds innovation, and strict verification breeds trust. It leaves me with one final thread to pull on, something for you to mull over as we wrap up this deep dive. Think back to the complexity of that gritty mechanic loop. If a self-modifying agent can teach itself to conquer formal Olympiad-level math by banging its head against an untrickable verifier, catching explicit errors and patching its own logic, imagine dropping this exact same architecture into the world of quantum computing code.
Oh.
Right. Right now, human engineers struggle to even hold the sheer mathematical complexity of quantum algorithm in their heads. We are trying to build the sub-goals and the elegant logic ourselves. But maybe we aren't the ones who will write the next massive breakthrough in quantum algorithms. Maybe we won't carefully design the workflow at all. Maybe our job is simply to build a sandbox, define the strict laws of quantum physics in a verifier, turn on the co-evolving treadmill, and watch the AI evolve the tools to discover the algorithms for us. Something to think about until our next deep dive.